Let me tell you something that might bother you a little bit. You think you're solid. You think when you knock on a table, you're hitting something real, something substantial. But here's the thing, you're almost entirely nothing. I mean that quite literally. About 99.999% of you is empty space. Or at least, that's what we used to think. The truth is much stranger, and I want to take you through it because once you understand what's really going on between the atoms, you'll never look at anything the same way again. I remember when I first started thinking seriously about this. I was a young man, maybe 23 or 24, and I was sitting in my office at Princeton trying to understand the structure of matter. Everyone knows about atoms by now. You learn about them in school, little balls with a nucleus in the middle and electrons orbiting around like tiny planets. It's a nice picture. Very clean. Very wrong too, but we'll get to that. The thing that struck me was this question. If atoms are mostly empty space, why does anything feel solid? Why can I push on this desk and not have my hand go right through it? You see, the numbers are absolutely staggering when you really look at them. Let me give you a sense of scale that I think makes this visceral. Imagine you took a single atom, let's say a hydrogen atom, the simplest one, and you blew it up to the size of a football stadium. You know, one of those big ones that seats 100,000 people. Now, in this enormous stadium, where would the nucleus be? It would be a tiny little marble sitting on the 50-yard line. That's it, one marble. And the electron? It would be a speck of dust somewhere out in the stands, orbiting around. Everything else, the entire volume of that stadium, all that space between the marble and the speck of dust, that's the inside of the atom. And here's what really gets you. If you made everything in that stadium proportional, the marble and the dust speck together wouldn't even account for 1/trillionth of the stadium's volume. The rest is, what? Nothing? That's what people used to think. Complete emptiness, a perfect vacuum. And if that were true, you'd expect some very strange things to happen. You'd expect, for instance, that matter should be incredibly compressible. Just squeeze out all that empty space. You'd expect that things could pass through each other if you lined them up just right. But none of that happens in ordinary life. Why not? This is where it gets interesting. You see, that empty space isn't empty at all. And understanding what's really there took us decades of the most careful thinking in the history of physics. Let me back up a little and explain how we got to this understanding. In the old days, I mean really old, before quantum mechanics, people thought of atoms as little solid balls. Democritus and those Greek fellows had the right general idea, but they imagined atoms as tiny indivisible chunks of stuff. Then we discovered the electron in 1897, and suddenly atoms had internal structure. They weren't simple anymore. Rutherford did his famous experiment around 1911, shooting alpha particles at gold foil. Most of them went straight through, which was already shocking because gold looks pretty solid, right? But every now and then, an alpha particle would bounce back as if it had hit something hard. Rutherford said it was like shooting cannonballs at tissue paper and having some of them bounce back at you. That's when he realized that almost all the mass of an atom is concentrated in this tiny, tiny nucleus. So we had this picture, dense nucleus, orbiting electrons, and a whole lot of nothing in between. But then quantum mechanics came along and made everything more complicated, and more beautiful, I should add. You see, the first problem is that electrons don't really orbit like planets. That was just a convenient picture. In classical physics, if electrons were orbiting the nucleus, they'd be constantly accelerating, because circular motion is accelerated motion, and accelerating charges radiate energy. They'd spiral into the nucleus in a fraction of a second. Everything would collapse. Obviously, that doesn't happen, so something was wrong with our picture. What quantum mechanics told us is that electrons don't have definite positions. They exist in what we call probability clouds or wave functions. The electron isn't orbiting in a circle. It's sort of smeared out in this fuzzy cloud around the nucleus. Where exactly is it? Nowhere, specifically. Everywhere, probabilistically. It's not that we don't know where it is. It genuinely doesn't have a definite location until you measure it. Now, this might seem like a technical detail, but it's actually crucial to understanding what's between the atoms. Because if the electron isn't a tiny ball zipping around, but instead a kind of wave spread throughout the atom, than what we call empty space is actually filled with. Well, with this probability, with the electron's wave function, with something quantum mechanical. But wait, it gets even stranger, because the electron isn't the only thing filling what looks like empty space. There are these things we call quantum fields, and they're everywhere. Let me try to explain this because it's really quite remarkable. In modern physics, quantum field theory, which is our best description of reality at the fundamental level, particles aren't fundamental, fields are. What do I mean by that? Well, think about it this way. Imagine the whole universe is filled with invisible fields, like an ocean of water that extends everywhere. These fields are always there, always present, filling every bit of space. When the field gets excited in a particular way, when there's a certain pattern of vibration, we see that as a particle. An electron isn't really a tiny ball. An electron is an excitation of the electron field, a ripple, a vibration, a pattern in this underlying thing that permeates all of space. Same with quarks, same with photons, same with all the particles. They're all vibrations in their respective fields. So what's between the atoms? Fields, quantum fields. The electromagnetic field is there, the electron field is there, the quark fields are there, the Higgs field is there. They're all there, filling what we naively thought was empty space. And here's the thing, even in what we call a vacuum, the most empty vacuum you can possibly imagine, these fields are still there. They're at their lowest energy state, their ground state, but they're not gone. They're still fluctuating. This is what we call vacuum fluctuations, or zero-point energy. Even in the emptiest possible space, there's still stuff happening. Virtual particles are popping in and out of existence constantly, pairs of particles and antiparticles appearing from the vacuum, existing for a tiny fraction of a second and then annihilating each other. It sounds crazy, but we've measured the effects. The Casimir effect, for instance, is a measurable force between two metal plates placed very close together caused by these vacuum fluctuations. It's real. So the nothing between atoms isn't nothing at all. It's a seething, bubbling quantum sea of fields and virtual particles and fluctuations. It's incredibly active, even when there's nothing there in the classical sense. But okay, you might say, that's all very interesting philosophically, but it still doesn't answer my practical question. Why don't I fall through the floor? If atoms are mostly these quantum fields and probability clouds, why does the floor feel solid? This is where it gets really beautiful. The answer has almost nothing to do with particles bumping into each other like billiard balls. The answer is electromagnetic forces. You see, when you press your hand against a table, what's actually happening? The atoms in your hand are getting close to the atoms in the table. As they get close, the electron clouds of those atoms start to overlap. Now, electrons are negatively charged, and negative charges repel each other. But that's not the main thing stopping you. The main thing is something much more quantum mechanical. There's a principle in quantum mechanics called the Pauli exclusion principle. It says that no two fermions, and electrons are fermions, can occupy the same quantum state. When you try to push the atoms of your hand into the atoms of the table, you're trying to force their electrons into the same space, the same quantum states, and nature says no, absolutely not. It creates an enormous repulsive force, what we call degeneracy pressure or exchange force. This is the same force that keeps white dwarf stars from collapsing under their own gravity. It's incredibly powerful, and it's entirely quantum mechanical. There's no classical analog for it. So here's the picture. You're not touching the table. Not really. The atoms in your hand never actually contact the atoms in the table. They get close, about an angstrom apart, which is a 10 billionth of a meter, and then these electromagnetic and quantum mechanical forces create a barrier that feels like solid contact. You're hovering above the table, levitating on an electromagnetic cushion. Everything you've ever touched, you've never really touched at all. Let me say that again because I think it's wonderful. You have never touched anything in your life. Not your mother's face when you were a baby. Not the hand of someone you love. Not the ground beneath your feet. It's all electromagnetic repulsion, happening at incredibly small distances, creating the illusion of contact. Now, you might wonder, if that's true, why doesn't light pass through us? Light is electromagnetic radiation, right? And it passes through glass, which is made of atoms just like everything else. Why not through people? The answer is that atoms absorb and re-emit light at certain frequencies. When light hits your body, the electrons in your atoms absorb the photons and then re-emit them in various directions. Some wavelengths get absorbed completely, that's why you're opaque to visible light, but you're transparent to other wavelengths. X-rays, for instance, pass right through your soft tissues because their wavelength is so short that most of your atoms don't interact with them. Only the denser atoms in your bones absorb them, which is why X-rays show your skeleton. So your solidity is actually quite selective. To certain wavelengths of light, you might as well not be there. To a neutrino, those ghostly particles from nuclear reactions, you barely exist at all. Billions of neutrinos from the sun are passing through your body every second, and they don't even notice you're there. To them, the Earth itself is mostly transparent. This starts to make you wonder about the whole concept of matter, doesn't it? What does it even mean to say something is solid or real? Here's what I think. We've evolved to perceive the world in a particular way because that perception helped our ancestors survive. They needed to know that falling off a cliff was bad, that rocks were hard, that water was wet. They didn't need to know about quantum fields or electromagnetic repulsion. So our brains built a model of reality that's useful at the scale we live at. At our scale, things look solid, colors look real, objects have definite boundaries. But that's just a model. A very good model for navigating the world at human scales, but still a model. When you look closer, much closer, reality is completely different. Atoms are mostly probability clouds in quantum fields. Solid matter is electromagnetic repulsion between electron clouds. Touch is levitation at very small distances. Everything you experience as solid, permanent, and definite is actually dynamic, probabilistic, and interconnected. And I find this absolutely beautiful. Some people get upset when you tell them that they're mostly empty space or that they've never really touched anything. They feel like you're taking something away from them, making reality less real somehow. But I think you're adding something. You're replacing a simple, boring picture with something much more interesting. Think about what we've learned. The space between atoms isn't empty. It's filled with quantum fields, the most fundamental objects in the universe. The forces holding you together are the same forces that govern stars and galaxies. The electrons in your body obey the same Pauli exclusion principle that keeps white dwarfs from collapsing. You're connected to the whole universe through these fundamental physics. And here's something else that I think about sometimes. Those quantum fields we talked about, the electron field, the quark field, all those fields, they're not inside space. They are space. Or at least, they're inextricably woven into the fabric of space-time itself. When you ask what's between atoms, you're really asking about the fundamental structure of reality, and we're still learning the answer. Modern physics is pushing even further. String theory, loop quantum gravity, various approaches are trying to understand what happens at the smallest scales, smaller even than atoms, smaller than protons and neutrons, smaller than quarks. At those scales, space itself might break down. It might become discrete, granular, something completely unlike the smooth emptiness we imagine. What I'm telling you is that the deeper you look at the question of what's between atoms, the more profound the answer becomes. It starts as a simple question about empty space and ends up being a question about the nature of existence itself. Now, I want to leave you with one more thought. Everything I've told you about atoms, about fields, about forces, we figured out by being curious, by not accepting the obvious answer, by looking closer. The ancient Greeks looked at matter and said it must be made of atoms. Rutherford looked at atoms and found the nucleus. We looked at the nucleus and found quarks. Who knows what we'll find next? The universe is not obligated to make sense to us, but somehow it does. Somehow, when we look carefully enough, when we think rigorously enough, patterns emerge. Laws become clear. Understanding happens. That, to me, is the greatest mystery of all. Not what's between the atoms, but that we can figure it out in the first place. You're 99.999% empty space. But that empty space is the most interesting nothing you could possibly imagine. It's where the quantum fields live. It's where the fundamental forces do their work. It's where reality happens, and you get to be part of it. So next time you knock on a table and it feels solid, remember, You're feeling electromagnetic forces transmitted through quantum fields across chasms of relative emptiness. You're feeling the universe's fundamental laws in action. You're feeling physics. And I think that's pretty wonderful.